Welcome to another Mathologer video. Today I'd like to tell you about a bunch of very paradoxical properties of the so-called harmonic series. This monster is one of the most iconic infinite objects in mathematics and has been investigated for hundreds, if not thousands of years. Of course, everybody who knows some calculus will be familiar with some basic properties of the harmonic series. However, most of its really amazing paradoxical properties even many calculus professors don't know. The reason why I'm telling you about the harmonic series today are some more counterintuitive facts that were only discovered recently and that I only found out about 2 months ago. This video has 6 chapters, each with its own highlights. Let's have a vote at the very end to figure out which of these highlights you like best. Will be interesting, and by participating you'll automatically enter into a draw for a chance to win a copy of one of my books. As a bit of a warm-up, let's engage in a little thought experiment. Over there I've put weights of 1 and 2 kilos on a simple balance. Let's assume that the gray bar does not weigh anything. Remember, thought experiment, we can do this. If I remove the supporting hands, will things stay balanced? Well, obviously not. The red 2 is heavier, so it will go down, like that. So to balance things I have to move the pointy fulcrum to the right. But where exactly do I have to put it? Now, if you're familiar with Archimedes' law of the lever, you shouldn't have any trouble figuring this out for yourself. Anyway, the answer is 1/3 from the right. Now here's a nice two-glance way to see that this is really true. Put the 2 kilo weight on a little tray, like this. Again, we'll assume that the tray does not weigh anything. Thought experiment, remember? Now split the 2 kilo weight into 2 1 kilo weights. Keep moving them apart up to here. Obviously, the combined center of mass of the 2 1 kilo weights is still where it used to be, there, right in the middle. On the other hand, all the 3 1 kilo weights are now equally spaced. Can you see it? There, the spacing on the left is 2/3. And the spacing on the right is 1/3 plus another 1/3 mirrored over is 2/3. But then the combined center of mass of the 3 equally spaced 1 kilo weights is right in the middle. That is exactly at the 1/3 mark from the right. A very, very pretty two-glance proof, don't you think? And the whole thing generalizes nicely. If instead of a 2 kilo weight we have a 3 kilo weight on the right, then the balancing point is 1/4 from the right. There. Put the tray, spread them out, equally spaced, right in the middle. Works. I like this stuff. And with a 4 kilo weight on the right, the balancing point is at 1/5. Okay, when I teach the harmonic series at uni, I usually motivate it with a nice real-world puzzle, versions of which you may encounter in many science museums. The brown blob over there is supposed to be the edge of a cliff. Now, add 20 equal rectangular blocks to the scenario. What we want to do is to rearrange the blocks into a stack with as large an overhang as possible. What do I mean by this? Well, I could simply push the whole stack to the right like this. This will create this much of an overhang. There, the green bit, that's the overhang. Can we do better? Yes, for example, we can push out the 1 block on top just a little. There, now the green overhang is larger. Of course, we've got to be careful. Push things over too far and the stack will topple over. And since the blocks are not connected to each other, the toppling can happen at any level. For example, right up there. So what's the furthest overhang we can create? I know, hard to tell given only what I've told you so far. Well, so as usual, let's look at some small stacks first to build up some intuition. You know the drill, right, from last time? Now, there, a stack with just 1 block. How far can we push this block to the right? Easy. The center of mass of this block is right in the middle. And the block will be stable as long as the center of mass is above the cliff. This means we can push the block all the way up to here. Now, let's say our blocks are 2 units long. then our maximal overhang is half that, so 1 unit overhang. Okay, what about stacks consisting of 2 blocks? Well, with 2 blocks, we can definitely also get a 1 unit overhang, right? Just slide the second block in like this. There, that obviously works. A 2-block stack with an overhang of 1. But we can definitely do better, because the center of mass of the whole 2-block stack in front of us is right here in the middle. Well, because the whole thing is symmetrical, it has to be in the middle, right? And this means that we can slide the whole thing further over to the right up to this point, right? The center of mass of the whole stack is above the cliff edge, and so nothing will fall down. What's the overhang now? Well, the one from before plus 1/2. And now we just repeat to get larger and larger overhangs. So first, add a 3rd block in like this. Next, find the center of mass of this new 3-block stack. Now, unlike in the cases of just 1 and 2 blocks, where everything was nice symmetrical, it's not clear where the center of mass is. However, using our warm-up exercise, we can easily figure out its location. So, we can think of our 3-block stack as consisting of 2 parts. The new block highlighted in blue and the old 2-block stack. Now, the center of mass of the 2-block stack is already part of the picture. The center of mass of the blue one is here, right in the middle. How far apart are the centers? Well, that's half the length of the blue block, so that's 1. Next, our 2 stack weighs twice as much as the blue block. And this means we're dealing with exactly our warm-up setup. And this means that the combined center of mass of the 3-block stack is 1/3 in from the cliff edge. There. Nice animation. Nice. Now push to the right like this and we get an overhang of 1 plus 1/2 plus 1/3. Repeat again. There, slide in, find the center of mass. Nice animation again. And yes, slide over. And at this point, the overhang is 1 plus 1/2 plus 1/3 plus 1/4. And we now know exactly how this will continue. However, also notice that at this point, the top block is completely beyond the cliff edge. And this is pretty amazing, isn't it? Challenge for you, actually perform this experiment. So use identical brick-like objects like books to build a stack at the edge of a table in which the top brick completely clears the table. Link to a photo of your little stacking miracle in the comments. Pretty tough challenge. Anyway, rinse and repeat and we get this remarkable leaning tower. And the overhang we can achieve this way with 20 blocks is, well, 1 plus 1/2 plus 1/3 all the way to 1/20th, which is approximately 3.6. Very cool. What I've just shown you is a mythologization of a construction that's at least 170 years old. These days, the stack over there is often referred to as the Leaning Tower of Lire. This name was coined by the physicist Paul Johnson and was the title of a note by him that appeared in the American Journal of Physics in 1955. There, that's the article. The lire in the title was the name of the Italian currency prior to the introduction of the euro, and in his paper, Johnson actually plays with a stack of coins rather than a stack of bricks. Anyway, now a very natural question to ask is, how much of an overhang can we produce if we have an unlimited supply of blocks? To answer this question, we have to evaluate the sum of the harmonic series. There she is, the lead character in today's tale of mathematical mystery. I'll puzzle out the sum together with you in a moment, but not before I say a little more about our original puzzle to find a maximal overhang by stacking these 20 blocks over there. I'm fairly sure that 99% of all the people who are familiar with this leaning tower are under the impression that this tower produces the largest possible overhang using 20 blocks. This is not the case, not even close. Want to see what the optimal stack really looks like? Ready to be disgusted? Here's the optimal stack, which was only discovered something like 10 years ago. The same 20 blocks, but reaches out much further. And ugly as hell, right? And didn't they always tell you that all optimal maths is automatically beautiful? Nuh-uh. While you often encounter beauty in the optimal, this is definitely not always the case. But of course, beauty is in the eye of the beholder, and there's definitely a lot of ingenuity to be admired here. For example, the use of counterweights and bridging weights to weigh down pieces that would otherwise fall down. What the presence of these bridging pieces also implies is that you cannot actually build this weird stack layer by layer from the ground up, right? Building up to here, the piece in front would definitely fall down. Now, whenever I talk about this, someone will ask whether it is at least true that the leaning tower is the optimal stack if we allow only one brick per layer. And this is actually true, although a correct proof that this is true for all possible numbers of bricks was only nailed down in 2018 by David Treby, somebody from Monash here, in an article in the American Mathematical Monthly. That this maximal overhang property is not completely obvious is hinted at by the fact that there is actually another one block per layer stack that has exactly the same overhang as our leaning tower of Lire. Again, hardly anybody seems to be aware of this. Have another look at the two top blocks. Can you see where I'm going with this? Center of mass right in the middle. Well, simply flip them like this and you get that second maximal stack. Cute, right? If you're interested in chasing down this particular rabbit hole, I've linked to some nice links in the description to get you started. So we can arrange for one complete brick to be beyond the cliff edge using 4 bricks. How can you do the same with only 3 bricks? Give your solutions in the comments. Okay, so we would like to know how much of an overhang one of our towers of Lire can have if we have an unlimited supply of blocks. To answer this question, we have to figure out what the sum of the harmonic series is. Well, let's start adding. Okay, so we are adding more and more positive terms, and so obviously these partial sums will get bigger and bigger. This means there are really only 2 possibilities. One, these partial sums converge to a finite number, which we would then declare to be the sum of the series, or the partial sums explode to positive infinity. Which one is it? Obviously, many of you will know the answer, but imagine for the moment that this is the first time you see the series. What would you bet your life on? Finite or infinite sum? Well, the terms we're adding get smaller and smaller and amount to closer and closer to nothing. So shouldn't the partial sums settle down to something finite? Just like for some other famous subseries of the harmonic series, like this one here. What's the sum of this one? Well, pretty obvious. Yeah. So there, infinitely many positive terms adding up to something finite. What about the sum we're interested in? Well, let's not drag it out any further. Turns out the harmonic series explodes to infinity. And the first, in my opinion, nicest proof of this fact goes back almost 700 years and is due to the French bishop Nicole Oresme. Clearly some posture problems due to excessive obsessing with mathematics. Okay, here's this proof animated as best as I can. Enjoy! An absolute gem of a proof, don't you think? Of course, what this implies is the leaning tower paradox. That, at least in theory, we can make our overhang as large as we wish by adding more and more blocks. Marvelous stuff, isn't it? There are actually a couple of other spectacular real-world paradoxes that are based on the fact that the harmonic series is exploding. For example, if you have not heard of the worm on a rubber band paradox, definitely check out the links in the description of this video. And if you know of any off-the-beaten-track real-world harmonic paradox, please share it with the rest of us in the comments. Okay, what have we got so far? One-glance balancing, leaning tower of Lire, bizarre maximal overhang towers, and a 700-year-old proof by a bishop. What do you like best so far? Okay, so the harmonic series diverges to infinity, but it does so extremely slowly. Have a look. As you can see, the series really grows very slowly. That's 1,000,000 terms we've added here. How many terms do you think it takes for the partial sum to hit 100? That number was calculated for the first time in 1968 by the mathematician John W. Wrench Jr., which was a bit of an achievement at the time. Here it is. So to get to 100, you have to add in the order of 10 to the 43 terms. That's really mind-boggling, isn't it? Also, how did John Wrench figure out that exact number? Obviously, actually adding the first 10 to the 43 terms one at a time is completely out of the question. Even the most powerful computers would take gazillions of years to add up that many terms one by one. Well, maybe there's some kind of magical formula for the nth partial sum that allows us to solve for the answer. Such a formula would also allow us to figure out that all-important question: how much of an overhang a leaning tower of 1 Google blocks, that is 10 to the 100 blocks, will produce. Well, maybe not that important a question in itself, but formulas like this really are incredibly important. Anyway, let's hunt for such a magical formula. If you watched the last What Comes Next video, you know what comes next. We start summing again from the beginning, but this time write down the partial sums as fractions. Let's see whether we can guess a pattern that translates into a formula. Okay, here comes the dreaded question. Can you see a pattern? Well, looks like a complete mess, doesn't it? But there's something striking about all these fractions. Can you see it? No? Okay, here's a hint. What do all the numerators have in common? And what do all the denominators have in common? Yeah, of course, many of you will have spotted straight away that all the numerators are odd and all the denominators are even. Coincidence? I don't think so. In fact, if you keep on going, you keep getting partial sums that are odd divided by even fractions. Interesting, but so what? Well, actually, in terms of odd and even, there are 4 different types of fractions. Odd over even over odd, even over even, odd over odd. There's one thing that is special about odd over even fractions, and that is, well, think integers. If you divide an odd number by an even number, the result can never be an integer, right? Whereas with the other types of fractions, they can actually be integers in disguise. There, all those fractions are really integers in disguise. Nice little insight, isn't it? An odd divided by an even fraction cannot be an integer. That could be a starting point for a nice number magic trick. Have to ponder this. Anyway, once you notice this odd over even pattern in the sequence of partial sums, it's actually not hard to prove rigorously that in fact all infinitely many partial sums are of this form. With the exception of the first partial sum 1, of course, which is an integer. And this then also shows that apart from that 1 at the beginning, there are no integers among the partial sums. That's a pretty amazing result when you think about it. Right? So these partial sums creep up slower and slower with smaller and smaller increments. On the way to infinity, they pass every single one of the infinitely many integers and manage to miss them all by minuter and minuter amounts. Amazing, isn't it? But in fact, something even more remarkable is true. Add up a randomly picked couple of consecutive terms of the harmonic series, like these ones here, consecutive is the important bit here, then it can be shown that all of these sums combine into odd over even fractions and are therefore never integers. The first proof of this fact was published in 1918 and is due to the Hungarian mathematician József Kőszeg, the very friendly looking guy on the white chair in the picture. That's a very typical mathematician group photo 100 years ago. All men, ties and suits, and no t-shirts. Times have definitely changed. Okay, to finish off this chapter, here is another challenge question for you. Can you write the numbers 2 and 3 as sums of reciprocals of distinct positive integers? I guess I got a bit sidetracked there. Still, I think this detour was totally worth it. And this is also a nice example how scientific discovery works. You don't always find what you're looking for. Anyway, remember what we set out to find at the beginning of the last chapter was an easy formula for the nth partial sum of the harmonic series. The usual approach to look at a couple of small examples to try and spot a pattern that amounts to a formula actually does not work for the harmonic series. But there is another very nice and natural way to approach this problem. 1, 1/2, 1/3, 1/4, 1/nth. Doesn't this cry out for us to ponder our sum in terms of the function 1 over x? Well, let's plot it. Where are the terms of our sum hiding in this picture? Well, plug in 1. 1 over 1 is 1, so there is 1. Obviously that blue segment is 1 unit long, but there's another 1 hiding here, a 1 unit area. Can you spot it? There, that's square. 1/2 is here, and as an area here, 1/2 times 1 is 1/2, and so on. And so there, that's a simple visual area counterpart to the harmonic series. Of course, there is another area in this picture that cries out to be highlighted, that area under the curve. But how is that going to help? Well, we're chasing the partial sums of the harmonic series. Let's focus on a small example. 1 plus 1/2 plus 1/3 plus 1/4 is equal to the blue area. Turns out that there's a really easy formula for the corresponding area under the curve. Integral baby calculus 101, a lot of you will have done this in school, tells us that this area is exactly equal to the natural logarithm of 5. And of course that means that our partial sum is approximately equal to that logarithm. In general, this approximation looks like this. How much of a difference is there between the left and right sides? Well, that difference is the area of the remaining blue bits sticking out on top. And luckily, these blue bits don't add up too much. Let me show you. See that 1 times 1 square over there? Well, all the blue bits fit in there. And so the sum of the blue bits, the difference up there, is less than 1. And that's important, no matter how humongous the partial sum is. In fact, this tethering of the logarithm and the partial sum immediately implies another proof of the fact that the harmonic series explodes to infinity. Right? Since the logarithm explodes to infinity, the tethered partial sum gets dragged along to infinity. It doesn't have a choice at all in this matter. Anyway, since for large partial sums an extra 1 doesn't really matter, for all intents and purposes, the nth partial sum is equal to the natural logarithm of n plus 1. Having said that, we can still improve this simple, very good approximate formula dramatically with very little effort. Notice that really all infinitely many blue bits fit into the square on the left. This means that all the blue bits add up to a number less than 1. This number has a special name. It's called gamma, or the Euler-Mascheroni constant, or simply Euler's constant. Oh, there's Euler again. Can't escape him, right? Another challenge for you. Okay, so gamma is less than 1. It's obvious, right? But can you also see at a glance that gamma has to be greater than 0.5? If you can, tell us why this is obvious. Anyway, Euler was the first to investigate gamma around 1734 and calculated its first 5 decimals. Gamma is one of those mathematical superconstants that just like pi, phi and e pops up all over the place. Just as a little teaser, here is one of my favorite identities involving gamma. There, e, gamma and all the prime numbers in one formula. How crazy is that? Anyway, here is a super nice trick. Let's add gamma to our approximate formula for the partial sums of the harmonic series. Here's what the sum corresponds to in the picture. So the sum is exactly equal to the pink partial sum 1 plus 1/2 plus 1/3 plus 1/4 plus a tiny portion of gamma corresponding to the extra blue bits petering off to the right. When you think about this, this is really an amazing formula. As n, and with it the partial sum, gets huger and huger, this formula approximates the partial sum better and better. That's the exact opposite to what most formulas approximating exploding sums usually do. Just two examples to show you how amazing this formula really is. For n is equal to 5, we get this. So in terms of correct digits, the formula gets the integer part of the partial sum right, but no decimals. Now here's what you get for n is equal to 500,000. That's already 5 correct decimals. And it really gets better and better the larger n is. Absolutely marvelous, isn't it? To finish this chapter, let me tackle those two questions that we set out to answer using our formula. Remember that humongous exact number of harmonic terms you have to add to get a sum exceeding 100, that number John Wrench calculated? What does our formula suggest this number is? Well, we want 100. Let's solve for it. There, autopilot. And, well, if you actually evaluate the expression on the right, for example, in Mathematica, you arrive at a number that's just shy of John Wrench's exact number. According to Mathematica, the difference is about 0.63. Pretty good, huh? Our gamma is really a very magical constant. In fact, John Wrench's proof that his number is based on our formula, starts with our formula. Of course, we can also use our formula to figure out how much of an overhang a leaning tower with n blocks can produce. So how about the Google blocks, for example? Well, the natural logarithm of 10 to the 100 is 230 and a bit units. This thing really grows very slowly. Well, that's logarithmic growth for you. In comparison, it has been shown that there exists a positive number c such that by using crazy towers, an overhang of c times cube root of n is achievable for large n. That's exponentially better than logarithmic growth. Nobody knows exactly what the absolute best crazy tower looks like for large numbers of blocks, but one not so crazy family whose overhang grows like cube root of n are these parabolic towers that were discovered by Mike Peterson and Yuri Zwick around 2009. That example over there consists of 571 blocks and produces an overhang of 10 units. The smallest leaning tower that has this overhang contains 12,367 blocks. Good stuff. And there are still lots of nice open problems that need to be sorted out, maybe by you. So to finish this chapter, let me at least mention one more super interesting fact about gamma. Since you're watching this, you're probably all aware of the fact that there is a mysterious and important connection between the sum of the positive integers, 1 plus 2 plus 3, and the number minus 1/12. Despite what some people claim, this wonderful relationship is not an equality. Now, when we dig deeper, we find that in a very precise sense, minus 1/12 is to the sum of the positive integers what gamma is to the harmonic series. The sum of the reciprocals of the positive integers. I don't have any time to elaborate on this today. If you'd like to do a bit of research on your own, Google Ramanujan summation and find out why the Ramanujan sum of 1 plus 2 plus 3 is minus 1/12 and the Ramanujan sum of the harmonic series is gamma. Okay, what have we got so far? One glance balancing, leaning tower of Lire, bizarre maximal overhang towers, a 700-year-old proof by a bishop, no integers among the partial sums, and magical approximate formula, and of course gamma. And I even managed to squeeze minus 1/12 in. What do you like best so far? Remember, there will be a vote at the end. Okay, final chapter. To finish off, let me just tell you about that other remarkable harmonic fact that I only found out about 2 months ago and that inspired me to dedicate this video to my good old friend, the harmonic series. The harmonic series is the sum of sums in the sense that it contains many very important infinite series. For example, there's the geometric series of the powers of 1/2 there, which sums to 2. Then there's Euler's super famous sum of the reciprocals of the squares, the reciprocals of the force powers, and in general all those other reciprocals of integer powers series that are part of the Riemann-Zeta function. Then there is E as a sum of the reciprocals of the factorials, and so on and so forth. I've talked about these and many other famous subseries of the harmonic series in previous videos. Now obviously there are infinitely many subseries contained in the harmonic series, summing to infinitely many numbers, and so a natural question to ask is whether every number is such a sum. What do you think? What's your gut feeling? The answer is yes. Every positive number occurs as a sum of infinitely many subseries of the harmonic series. This is actually very easy to see. Let me quickly show you how you can find a subseries that sums to our new favorite magic number gamma using a greedy algorithm. Works for any other positive number. As the first term of a subseries that will sum to gamma, choose the largest harmonic reciprocal less than gamma. Well, gamma is 0.57, and so the largest harmonic reciprocal less than gamma is 1/2. The next term of our subseries is the largest harmonic term that when added to 1/2 gives a sum less than gamma. That happens to be 1/13. There. That sum is just a little bit less than gamma. And you just keep on going like this, always at the largest possible harmonic term that gives you a sum less than gamma. This will automatically generate a subseries containing infinitely many terms that add very rapidly to gamma. Nice and super simple, huh? This is an example of a greedy algorithm in action. We always greedily go for the largest possible reciprocal that fits. Of course, apart from all those subseries with finite sums, there are also plenty of subseries that, just like the harmonic series, diverge to infinity. For example, the sum of the reciprocals of the even number diverges. Pretty obvious, because this series is also just the original series, there's the original series again, multiplied by 1/2. So the sum of the reciprocals of the even numbers is 1/2 times infinity, which is still infinity. What about the sum of the reciprocals of the odd numbers? Well, the first odd reciprocal 1 is greater than the first even reciprocal 1/2. The second odd reciprocal 1/3 is greater than the second even reciprocal 1/4, and so on. And so the sum of the odd reciprocals is greater, term by term, than the infinite sum of the even reciprocals, and so also has to be infinite. Okay, maybe that's not that terribly surprising. Here's something trickier. How about the sum of the reciprocals of the primes? Finite or infinite? Well, what do you think? Of course, there are infinitely many primes, but they are pretty sparse, with arbitrarily large gaps in between them. Does this mean the sum is finite? Well, those of you who watched my video on Euler's product formula for the Riemann-Zeta function may remember that we proved, following Euler's footsteps of course, that the surprising answer is this sum is infinite. Really not obvious at all. Let's see how much of an intuition you've developed for these infinite sums. I'll show you a couple of subseries and you try to guess whether they have a finite or infinite sum. Ready? Okay, that's the full harmonic series over there. First, let's skip every 10th term starting with 1/9. That takes out this infinite column of terms. Is the leftover series finite or infinite? You got it? Easy, right? This subseries must explode because, well, there are lots of ways to see this at a glance. For example, it must explode because it contains all the even reciprocals, which we've already seen do explode. For my second mystery series, I'm going to throw away all the reciprocals of numbers that contain the digit 9. Okay, so that gets rid of the last column again. Right? All those have a 9. But of course, there are numbers other than these that feature the digit 9. For example, all the guys at the bottom there. Okay, no more 9s as digits left over. finite or infinite? Imagine your life depends on getting this right. You've got 5 seconds. 5, 4, 3, 2, 1, 0. You got it? Well, based on past experience asking this question, almost all of you will have gone for infinite, which is wrong, believe it or not, but this one has a finite sum. I first encountered this no-9 sum in the second week at uni in Germany, a couple of ice ages ago. They actually gave it to us as a homework exercise. This fun series is known as Kempner series, named after the mathematician Kempner, who published a finiteness proof in 1914. What makes this counterintuitive results particularly memorable for me is that I did come with a finiteness proof myself as part of this homework assignment. I can't remember how I proved it, but I do remember that I got 0 marks because the marker could not be bothered to actually engage with my proof that was different from what was expected. I'll do a super nice animated algebra proof that the no-9 series has a finite sum at the end of this video. But just real quick, one way to intuitively see that Kempner's no-9 series may be sparse enough to allow for it to converge is to realize that the picture over there is a bit misleading, that in fact the vast majority of integers with large numbers of digits will contain a 9 among their digits, and therefore their reciprocals will not count towards our sum. Tristan, one of the 3 volunteers who helped me with proofreading and polishing my slideshows, suggested a nice visual way to illustrate this thinning out. Make the 10 times 10 picture over there a bit more squarish and color the part with the remaining reciprocals black. Let's pretend the upper left square is also black, makes for a cleaner argument, okay? Then up to that little fudging in the corner, the black area inside the big square tells us how many of the first 10 times 10 terms of the harmonic series are contained in Kempner's no-9 series. Zooming out, the corresponding picture for the first 100 times 100, that's the first 10,000 terms of the harmonic series, looks like this. More white than before, so the percentage of omitted terms has gone up. Interesting. Here's the picture for 1000 times 1000. That's the first 1 million terms of the harmonic series. The percentage of omitted terms has gone up again. Now 10,000 times 10,000. Looks the same, but it's not. On closer inspection, there are actually tiny white subdivisions of the little black squares that mirror the 9 times 9 subdivision that you're seeing in front of you. Like, for example, the little square right there. When you have a close look, it actually looks like this. Because of the presence of the white subdivisions, the little square is actually gray and not completely black, and so again, the percentage of white has gone up. As we zoom in, digit by digit, the subdivisioning continues, turning what you see in front of you into a fractal-like object. And the percentage of white will go to 100% as we push things to infinity. Pretty amazing, huh? Thanks again to Tristan for suggesting this fun visualization of the really dramatic thinning out of the harmonic series when we throw away all the reciprocals of integers that contain the digit 9. Makes the convergence of the series so much more believable. Not a proof, but as I said, I'll do an animated algebra proof at the end. Okay, everything I've told you so far I've known for many, many years. Now, what I stumbled across 2 months ago were a couple of articles by the mathematician and computer scientist Robert Bailey, full of very interesting and surprising results about the no-9 series and a whole universe of closely related crazy subseries of the harmonic series that I'd never heard of before. For example, it turns out that nobody actually knew the sum of the no-9 series until quite recently. What Kempner showed in his 1914 article was that the sum of the no-9 series is less than 90. How close is 90 to the actual sum? Well, although the no-9 series turned into being a bit of a celebrity among people in the know, nobody appears to have given this question any serious thought, until Robert Bailey did so about 30 years ago. He figured out that the sum of the no-9 series is approximately 22.92. At that point in time, he also figured out good approximations of the no zeros, no ones, no twos, etc. series. Here's a table from his article which summarizes his results. Why had nobody calculated any reasonable approximations before? Well, it turns out that all these missing digit series converge at a snail's pace. For example, for the no-9 series, the sum of the first 10 to the 28 terms is still less than 22, so not even close to what most of us would call a reasonable approximation of the true value of the sum. And so for these series it's also completely unfeasible to simply keep adding up terms until we get close to the true value. You really need a good idea to get anywhere with approximating these sums. More recently, Robert Bailey also managed to calculate similarly good approximations for other closely related crazy series like the no zeros and no nines series, so a couple of digits missing, not just one. The at least 10 nines series, so every term has at least 10 nines, the exactly 100 zeros series, and so on. Really impressive stuff, especially since most of these series converge much slower than the already very slowly converging no nine series. For example, the sum of the 100 zeros series is approximately 23.03. Also pretty amazing in another way when you think about it, right? The first term of the 100 zeros series is 1/1 Google, which of course is a crazy small number. And yet the sum of the series in which every term has exactly 100 zeros ends up being larger than the sum of the no nine series, which starts out with much larger terms. So how are these really good approximations calculated? Well, it's not that terribly complicated, but also quite nitty-gritty technical, so I won't go into details here. The basic idea is to exploit the patterns in these series in the calculations, the kind of patterns that were visible in Tristan's fractal, for example. For the keen among you, I've included some relevant links in the description of this video. Anyway, as you can probably tell, Robert Bailey's papers really made my day when I stumbled across them, and I hope I've been able to convey to you some of my excitement about these new and old insights into the nature of the harmonic series and infinite series in general. What I'll finish with today is a methodologized, slightly refined version of Kempner's original proof, which shows that the sum of the no nine series is less than 80. Watch it and afterwards cast your vote for the harmonic marvel in this video that you enjoyed most. What's most memorable? One glance balancing, leaning tower of Lire, bizarre maximal overhang towers, that 700-year-old proof, no integers among the partial sums, that amazing approximate formula, gamma, greedy algorithm, Tristan's fractal, Kempner's proof. Well, we really did cover a lot of ground. Cast your vote by leaving a comment within the first 2 weeks after this video went live for a chance to win one of my books. I'll then pick a random name among those who participated and the random book and will announce the winner as part of the 2020 Christmas video. Okay, now to finish, here's why Kempner's no ninth sum has a finite sum.